time. So,
well, I'm sure if everyone's enjoying the subject, it'll be absolutely fine anyway. But we are live, so here we are for another live Chargehead session, and it's all about batteries this week. And we've got Euan Mcturk on the side of me here. Hi, Euan. And yes, well, I thought, do you know what? It's time that we spoke all about batteries because it's a huge subject, and I think it'd be great to do a bit of a deep dive with the expert, Euan. So just a brief outline, Chargeheads is all about modified EVs, EV conversions, and every Thursday, 8 o'clock, we have a chat about all things electric. But we're going to focus, the agenda is going to be focusing on a little bit of the history of lithium batteries, where batteries are now, the future of batteries, talk a bit about safety and fires, no doubt. Everyone loves legacy media. They love a battery fire, don't they? I'm sure we'll talk about the best EV batteries. And not only that, but Euan has actually got quite a few EV projects as well, which are rather exciting. So no doubt we'll talk about that and a bit of degradation. Nothing like a bit of degradation in batteries as well. So, yeah, Euan, please tell the audience a little bit about yourself and a bit about Plug Life as well, and what got you into batteries and the forum of electric vehicles.
evening, everyone. Yeah, thanks again for having us on the program tonight. Loving it. Good to be on. So yeah, I'm Dr. Euan Mcturk. I'm a consultant battery electrochemist, and I've been working on and driving EVs since 2009, which is when I first properly encountered one, actually. So the background is I was doing my applied physics renewable energy degree at the University of Dundee, going into my honours year, trying to decide what I wanted to do for my honours project. And lo and behold, this 1999 Peugeot 106 electric pulls up outside the Harris building at Dundee Uni, all liveried up in University of Dundee stickers and things. They just managed to find one of these at the time 10-year-old NiCad powered electric vehicles. And I immediately knew, okay, this is what I want to work on. I don't know exactly how, but this is a cool thing. I didn't realize that EVs existed in Europe. You know, I'd briefly heard of the GM EV1, couldn't have told you what it was called. But yeah, here's a comparatively modern EV. So yeah, after a lot of nagging, I eventually was allowed to start working on it, and it was suggested that I should look at battery tech because that's the main bottleneck and where the research was starting to get quite exciting. And so I started researching lithium air cells, which were next generation novel cells that, if anything, had more in common with a fuel cell than a lithium ion cell. They were made of very cheap materials, really high energy density. There was talk at the time of like a 10 times boost in range versus lithium ion. So like 1,000 miles per charge, that sort of deal.
Wow.
Yeah. But as it transpires, well, I ended up doing my PhD in one of the leading battery research groups in the world, who was they were working on lithium air at the time. So Professor Peter Bruce was based at St Andrews at the time, had a research group of about 30 people. He now heads up the Faraday Institution. Very, very well respected electrochemist in globally, basically. So I was very lucky to work in his labs. And I was working on lithium air along with many fantastic colleagues, but I was coming at it from a physics perspective rather than a chemistry perspective. So, my knowledge was a bit of a well-attacked Jenga tower. And again, I'm incredibly grateful to my colleagues and to everyone I've worked with for filling in that knowledge. And to be fair, nobody knows everything, but such is my determination. I give it a darn good try. And I love learning about all sorts of different aspects of batteries. So whether it's and kind of renewables and decarbonisation and sustainability in general, but whether it's raw material supply chain, whether it's ethics, whether it's safety, recycling, end of life, and also obviously the fundamental: can we make batteries better? Can we boost the range? Can we improve charging times and so on? So yeah, I was kind of learning a lot of this on the side. The research group then moved to Oxford halfway through my PhD. So I started working with Professor David Howie as well. And his work was more on the kind of electronics, the battery management systems. that keep your battery packs in good condition, and also working on commercial lithium-ion cells. They were wanting to model how they degrade and use that to try and boost the understanding of battery tech, but also the improvement in performance of battery management systems. So we would take.
Sorry to interject there.
Sorry.
What year was that? Just so we can get an idea of timeline.
Yeah, so that would have been 2014 that I moved down to Oxford. I was there for just over a year. It was just that kind of final year of the PhD. But that was when everything really accelerated and a lot got done. I was very much there to put the work in. So some of my colleagues were really excited about the kind of collegiate system of Oxford, where you put on the Harry Potter sorting hat and you have to go into different colleges. Like, most universities, you are in the Department of Material Science, and then you are all part of the same university. But I was, for example, I was in the Department of Material Science, but I was at Linacre College, part of University of Oxford. So there was that kind of clique within the college, and you didn't really speak to anyone else from other colleges unless you happened to be in the same academic / PhD research group. So that was a bit odd, but to be fair, I was there to get the work done. And we published numerous papers together between the Bruce group and the Howie group, and I worked very closely with a fantastic chap, Christoph Burkle, who was doing his PhD. We'd actually bumped into each other back at Dundee Uni a few years ago, because he did a brief stint there whilst he was. It was kind of what do you call it? Not an Erasmus, something where basically come and visited the university for a few months during his undergrad. So it was like, no way, brilliant, good to see you. And we were just like that. Honestly, we were just so quick at bouncing ideas off of one another. He was doing the modeling side of things, and I was doing the sticking my hands in a glove box, surgically operating on a lithium-ion cell that was not designed to be operated on and then behave as if nothing had happened to it. And that allowed us to get information on what causes cells to fail. How do we stop them failing? How hard can you push them? Incidentally, I continued that work at WMG with Tajdin Amachayev, who I was also like that with. I've been very lucky with some of the colleagues I've had over the years, but Christoph, incidentally, now has his own company, Brill Power, that's doing amazing things with battery management systems, which are really good at extending the lifespan of battery packs, mixing and matching different chemistries, all sorts of clever tricks up its sleeve. But it's super advanced stuff.
I've heard of this, mixing, different chemistries, whether it's sodium with LFP, etc. What did you say the name of that company was? Brill Power?
Yeah, Brill Power. Yeah, based in Oxford. Wow. And they were basically founded by Christoph and some of the other Howie group PhDs from the same year, actually, the same cohort. So they've done really well out of that. They're very well respected for what they do. Their knowledge is incredible. Their product's incredible. Traditionally with the battery management system, you do not want to mix and match cells of different chemistries or capacities, because remember, the pack is as strong as its weakest cell. And when you're building up the pack in series, positive to negative, to get the right voltage, you could have some cells that have a huge amount of capacity, but it all comes down to which cell has hit its maximum voltage that it cannot go over, or it will get damaged during charging, and which ones hit its minimum voltage during discharging. Again, you don't want to take it right down to 0 volts on a lithium-ion cell, because you'll brick it. So there are clever ways and means that you can mix and match chemistries or different states of health. And there's a great deal of electrochemical alchemy that goes on at Brill Power, where they've found solutions to this. And that means that you can make much better use of supposedly end-of-life electric vehicle batteries in, for example, static energy storage systems. You can mix them together, and it works with the remaining energy that's available in each of those cells or modules, and manages to go harder on the ones that are capable of being pushed harder and back off the ones that are struggling a bit. And you just end up massively improving the lifespan of those cells, and therefore, massively increasing the lifespan of the energy storage system / application it's in, and therefore delaying the need to recycle them.
So you said that it extends the life. So, I mean, if you can give us an example. So, for example, if it's a Nissan Leaf battery, which is quite well known for its degradation, and let's say it's, I don't know, a 10-year-old Leaf battery, how long would again, this might be too specific. Let's say the battery's got 70% of its battery state of health left. I mean, how long could you use that battery as home storage or a number of things for business? I mean, what sort of longevity are we talking here?
Well, first and foremost, and obviously you'll know this as well, but just to point out that when an electric vehicle battery is determined as end of life when it reaches 70% of its original capacity versus new, that doesn't necessarily mean that it is genuinely at the end of its useful life in an electric vehicle. I mean, the biggest Nissan Leaf battery, 62 kilowatt hours, 230 miles per charge. So, you're looking at, what's that, about 160, 170 miles per charge when it's down at 70% state of health. You could keep running that, but bearing in mind the average round trip UK commute is 26 miles. When it eventually becomes useless for you, then in terms of that useful lifespan within a static energy storage system, the fact that an energy storage system has a much lower, more consistent load on the battery than the very dynamic, sharp acceleration, regenerative braking, kind of wibbly wobbly graph that you would see of power versus time for an electric vehicle, that means that you can get much greater lifespan out of a battery going into an energy storage application than in an electric vehicle. But we already know that electric vehicle batteries are lasting a lot longer than expected. So realistically, you could be measuring the lifespan of that static energy storage system in decades. And that's for a heavily degraded EV battery, it would need to be a really rubbish battery to struggle to get a decade's worth of useful use, even after it's been hammered in like a Nissan Leaf taxi for a good few 100,000 miles prior to that.
Yeah, I think it's going to be an interesting when the battery recyclers, which now can recycle up to 95%. I saw in recent social media news of all the precious metals, the lithium, etc. Is there a tipping point between, actually we really want to be able to recycle that battery because it's very valuable to the industry? It'd be interesting to see when that tipping point is, and whether it's actually better to recycle them rather than using them for second life battery storage. But it's the exciting things that that come about with batteries. There's so many different uses for this power, and power is something that I come across a lot in charging at the moment, and power is sometimes can be a big challenge, especially if you want the fast chargers that we sometimes deal with. But okay, no, it's great to get an overview. Euan, can you tell us? Wayne's got a question here on the subject of mixing batteries. Do you see LFP getting any better, or has it plateaued?
Oh no, LFP is going to get better. It's already getting better, and on that point, we've seen improvements in the actual energy density of the individual cells. So, the amount of watt hours per kilogram or per liter, which is arguably more important for electric vehicles because you're constrained by volume more than weight. But, how much space have you got to accommodate that battery? But also we're starting to see improvements in battery packaging efficiency, not just how much energy the individual cells hold. You can claw back even more efficiency by removing superfluous packaging, basically. So if you look at, for example, conventional battery packs, those are module to pack. So you've got your cells put into bite-sized modules, kind of shoebox size, or in the case of some Tesla modules, a meter-long fish finger size. They can be quite sizable. But those all get wired together in series to make a battery pack. But what you've got there is a bunch of metal or plastic boxes which have taken up some space. Yeah. So if you can do cell to pack, then you just wire all the cells together in series and you get rid of those individual boxes. And that means that you've dedicated more space to storing energy than space to storing the things that store the energy. And you can take that even further by doing cell to chassis, and you make the cells actually load bearing and part of the structural integrity of the vehicle, part of the crash protection as well. They kind of take some of those hits and absorb them in a way which is safe. And obviously there'll be a top and bottom to that battery pack at the very least, even though it's cell to chassis. And you ideally still need that to be able to be removed for servicing or replacement or battery swapping, especially if battery swapping starts to take off in Europe. It certainly is in China, but it's a very different market due to comparative lack of off-street parking and total reliance on public charging infrastructure as a result. But anyway, back on point, with cell to chassis, that's where it gets interesting, because again, you have further improved the range that you can achieve on a lithium iron phosphate battery pack. And that's why Tesla was first to jump with a modern EV that does 200 plus miles per charge using LFP. Certainly, your US and European automotive manufacturers would have laughed you out of the room in 2020 when you said, I'm going to make a 200-mile range using LFP. Tesla came along, said, hold my non-alcoholic beer. I'm going to buy these cells off of CATL and make a surprisingly energy dense battery pack. And it's only got better since then. And now we're starting to see even more companies switching to LFP, predominantly Chinese companies at the moment. So standard range MG4, all the BYD's electric vehicles, standard range Maxus vans, and of course the standard range Tesla Model 3 and Y. But more US and European automotive manufacturers are switching to LFP. Expect minimum ranges of about 200 miles per charge for most of them. They will continue to get better as we get better at packaging efficiencies and as we start to be clever with the anode negative electrode materials that we use. Because at the moment, we're generally using bulky graphite. And graphite is needed to stop lithium from creating these little branch-like growths called dendrites, because it doesn't plate evenly. If you were to use pure lithium on the negative electrode, it wouldn't plate evenly as it's charging and discharging. It would start to form these little growths, and they would short the cell, and obviously you'd end up with a heck of a lot of heat being generated and the inability to stop it. So what we do with that situation is we put graphite in there so that the lithium pigeonholes itself safely into the structure. But you require 6 carbon atoms per 1 lithium atom. So it's that carbon is just storing the stuff that stores energy. It's bulky. If you can replace it with silicon, which has its own issues, which are being worked through, we can talk about that in a minute if you like. But if you replace it with silicon, you only need 1 silicon atom to store 4 lithium ions. So massive improvement in energy density. Yes, you've still got a comparatively bulky cathode, positive electrode. Yes, you've still got a separator and a liquid electrolyte because we've not gone solid state with this particular tweaking of the chemistry, although you could do potentially. But what you've done is you've still managed to shunt a lot more energy into that cell. And you'll start to bring it comparatively close to, or certainly closer to NMC's energy density. That's lithium, nickel, manganese, cobalt oxide that's been used by pretty much every EV until the LFP Model 3. The other consideration is that you can tweak the LFP chemistry. So there are companies who are putting manganese in the lithium iron phosphate. Manganese is pretty abundant. I mean, that said, there is potentially going to be a supply shortfall because of the the ramping up of demand for it. It's just a case of getting the reserves out the ground. It's obviously the kind of mining and processing bottleneck that would be the concern. But if you put manganese in there, then you increase the voltage, the overall cell voltage. And that means, and because your energy stored is basically it's the voltage multiplied by the capacity in ampere hours. If you have a higher cell voltage, then you achieve a greater energy density. So LFP has a lower cell voltage because the potential is the kind of individual electrode voltage, which isn't technically true, but in layperson's terms, of lithium iron phosphate is lower than NMC. So you pair it with the same anode material, you get less voltage and therefore less energy density. But if but LMFP brings it up a bit closer to NMC, and then
that's the code. Is it L? What was it? L?
No, LMFP, manganese. So it's lithium manganese iron phosphate. That said, there are companies working on basically doping LFP with different metals other than manganese, but it's with the same idea of increasing the voltage. And that really means that you're starting to get close to what NMC can do. There are rumors that there's going to be LMFP coming to the Tesla Model 3 in the not too distant future. And if that happens, the standard range Model 3 will get tantalizingly close to 300 miles per charge.
Wow. That's impressive. I mean, I know that when we talk about all these different chemistries of batteries, it's improving all the time, which is great. NMC has got a lot of negativity from the legacy media and a lot of media around the cobalt that's in the batteries, but a lot of people don't realize, the cobalt, children in the cobalt mines, and a lot of people don't realize that cobalt is in many things. It's in your phone battery. It's in, it's used to desulfur fuel into oil into petrol. So it's great to see that the EV industry focuses on making it greener compared to a lot of other industries out there. So I think you mentioned graphite, and graphite, as I understand it, that has been quite a difficult material to get hold of until I think there was a recent discovery in Scandinavia where that was become, or I don't think it became more abundant. I think there was a way of producing it in a different, in a man-made way, I believe.
So with graphite, you've got your natural graphite resources, which are predominantly from China. There's a lot of just sort of natural graphite you can dig out of the ground, basically.
They've certainly got their fair share of the battery materials, haven't they?
Oh, yeah. China has basically monopolized a lot of the battery supply chain. And even if those raw materials do not exist in China in any great volume, China has gone in and built the infrastructure, invested in / bought out the companies in Africa, in South America, in Europe and the US as well. There's basically such a massive control of, in fact, there's very few materials where China doesn't have at least 50% of the kind of mining capacity. The processing capacity gets even higher. Things like manganese, you're over 95% of processed manganese comes out of China right now, which is why the Inflation Reduction Act in the US and the kind of EU rules of origin are starting to see things like, for example, manganese processing plants being built, which would have sizable capacity for this important material. We're going to see, the kind of electrodes material capacity for various different lithium-ion based chemistries, increasing to substantial volumes, but there will probably still be some reliance on China. Because they basically kind of looked in the early 2010s and went, where's transport going? Well, Japan says it's hydrogen, but we know that's nonsense. And, they've gone down the battery route and done it annoyingly well. And it's only recently that EU and the US have gone, oh, right, maybe we should do something about this. I
was sorry to interrupt you. And I just had a thought that I don't remember seeing any hydrogen Chinese cars.
Now, interestingly, there are some hydrogen EVs kicking about in China. You occasionally hear about a move towards hydrogen, but it's not like en masse. By a move towards it, we're talking like a handful of fleets experimenting with it. There is definitely not some sort of seismic wave of shift towards hydrogen. So the people who say, oh, it'll be batteries that will come along first and then it'll be hydrogen. Why would you do that when it requires 2.5 times as much electricity to produce hydrogen cleanly and then run it through a fuel cell, etc., versus just stuffing that electricity directly into a battery? Because, of course, that inherently means that your electricity costs for green hydrogen are 2.5 times as much. So it's going to be an inherently expensive fuel as well as an inefficient fuel. So, anyway, there's definitely markets where green hydrogen is needed. And Michael Liebrich has a brilliant hydrogen ladder. You know, the kind of energy ratings, the kind of A to G, the thing that you get on your fridge, that sort of thing. He's got a hydrogen ladder just like that, and it shows you where green hydrogen is irreplaceable and needed. For example, clean steel production without using coal, and where it makes absolutely no sense whatsoever, like, for example, heating homes. Heating homes is a ridiculous use of hydrogen, just because of how inefficient it is. Speaking as a very happy heat pump owner, okay, there'll be properties that aren't suited to heat pumps, but oh my goodness, the ones that do, and by the way, this house is an early 80s house. The insulation is mediocre at best, and my God, the heat pump is incredible. The house is always warm. The water is always hot. People who say, oh, it's lukewarm. No. Nice hot showers and all that. Nearly scalded my hands on a few occasions when doing the dishes and stuff. It is absolutely the way to go. And I think if I ran the maths on this previously, it's something like 6 times more heat that you get out of the same electricity through using heat pumps versus using green hydrogen in a boiler. 6 times as much, because you've had to waste energy through a very lossy step to produce green hydrogen and then put it through a boiler that loses a bit more energy, versus putting it into a heat pump, which turns 1 unit of heat into 1 unit of electricity into 3 units of heat scavenged from the air. It's incredible.
Plus the fact that they'd have to upgrade all the pipelines because hydrogen molecules are smaller, so there'll be leakages. And unfortunately, with hydrogen, you can't smell it and you can't see it till it's too late. And we, I'm well on board with that one. I think I have seen a lot less hydrogen stuff out there, but I think there are still a lot of people that think that that is the answer. You know, I think for a very small proportion of transport, you know, your combine harvesters and certain levels of transport specialists, I think maybe that could be an answer, but certainly not personal transport. And it's going to be very interesting with the heavy HGV, heavy goods trucks. You know, there's a lot going on with the ZERF, the EV charging for HGV in the UK, and yeah, there's a lot going on, which is really exciting.
I've got to give a big shout out at that point to Andy Salter from Freight Carbon Zero, who's got a fantastic website, newsletter, resource basically for anyone who's looking into HGV decarbonisation. And it's always a brilliant. It's Freight Carbon Zero, and it's Andy Salter who's at the helm of that. He writes a weekly newsletter, and then there's the kind of news website too. You know, very much right in the heart of the UK and beyond freight decarbonisation scene. And he always calls for CAM in the battery versus hydrogen debate for trucking, which is fair enough. You know, I can get on board with there being CAM about that, because it's not like a typical UK family car that's doing 8,000 miles a year where you absolutely do not need hydrogen for that. But with the kind of battery versus hydrogen debate, there is a third contender, which is also electric and is also battery, but it's battery swapping. And that it absolutely makes sense for logistics and for identical makes and models of vehicle within the same fleet that are doing the same routes day in, day out, where you know where they're going to need a top up. And I mean, that said, you know, we've got high power truck chargers that will recharge the truck broadly within a driver's tacho break, certainly is kind of longer lunch break. But if you look at what Janus is doing over in Australia, so they're retrofitting diesel trucks, diesel articulated lorry tractors to electric propulsion, and then they're putting in 2 swappable battery packs either side of it, almost like panniers.
It's impressive, really impressive.
Yeah. They swap them out with forklifts in under 10 minutes. That is less than the driver's tacho break. The truck is ready to go before the driver is. And those, by the way, are over 100-ton road trains. I think the latest one they've got, the original was like a 96-ton twin trailer, you know, like 44-ton each plus the lorry road train. You've now got the 3 trailer ones that Australia uses because they are a massive country and they need to move goods long distances. You've got these strategic swapping stations, which are powered by this punishing giant ball in the sky that Australia gets hitting it constantly. It just totally checks out. And we could do something similar here easily, because we are a tiny little island and we don't need, actually, you know, I mean, the ideal would be moving to overhead electrified freight, but that requires doubling up railway lines to improve capacity, because we also need to move passengers onto trains and off of cars and things like that. So yeah, there's so many different rabbit holes that you can go down, and as you can tell, I tend to kind of dip my head down quite a few of them when I'm trying to give a straight answer. I believe we were talking about graphite, and I'll come back to it now.
No, it's fine. It's fine. I'm soaking it all in.
Fair play. But I mean, so very quickly, so yeah, natural graphite. There's also synthetic graphite, and synthetic graphite requires needle coke, petroleum needle coke. So that comes out of an oil refinery. Basically, it's the really kind of thick, heavy stuff which, when you're refining oil, doesn't boil off. Kind of like bitumen, I guess. Anyway, there are very few refineries that do petroleum needle coke, and the only one in the UK is the Humber refinery. And that needle coke, which is this important precursor to make synthetic graphite, which is renowned for its quality, for battery materials, that currently gets exported to China. And bearing in mind that the Humber refinery isn't a million miles away from where Britishvolt was meant to be, and where there could yet be a gigafactory, touch wood, it would make so much sense to build a synthetic graphite processing facility pretty much next to the Humber refinery, using the petroleum needle coke from the Humber refinery, rather than shipping it halfway around the world for us to then buy back in the batteries of electric vehicles. We could make this stuff here. And I can tell you now that, especially with the Inflation Reduction Act and the EU rules of origin, even if we don't end up with a Britishvolt gigafactory nearby, and even if Tata, with their planned gigafactory somewhere in the south of England, says, do you know what, we've actually got enough graphite, thanks, I guarantee you that every last morsel of it will be bought up by some sort of gigafactory in the EU, UK, or US, because this is valuable material. And also you could power that using an abundant amount of renewable energy, because it's right next to the Creaky Beck substation, which is the landing point for the Dogger Bank offshore wind farm, which is several gigawatts of capacity. I'll get off my soapbox now, but that just shows you we've got so many pieces of the jigsaw here, and they've just not been put together. They do fit.
It is a massive frustration, and I know that you get involved in other things, which are certainly frustrations of mine. In the certain myths that get pushed out there. But funnily enough, one of the head guys of British Volt lives down the road from me, ironically. But yeah, it's a real big shame, because as you know, and myself and a lot of people in our community, we see where the transition is going in terms of transport, electrification. It feels like we are very much being left behind, and that is a massive that is definitely a rabbit hole that we could go down from a political point of view, but let's try and stay away from that one, otherwise we could be here until tomorrow. But yeah, so going back to your original electric car, the 106, wasn't it?
Yeah, Peugeot 106 electric, NiCad batteries, 12 kilowatt hours, 0 to 60 in yes, basically. Electronically limited to 260. I'm sure if it wanted to, you could just about squeak it up to the motorway speed limit. And about a 50-mile range, assisted by the fact that it had a petrol heater. So it was electric, it was fully electric propulsion, but you cheated with the cabin heating. Right. And it also had tartan seats, which were absolutely bitching. Best interior I've had of any car ever.
Any spinners on there?
Oh God, no, no, none of that. But it definitely felt thug life enough. To me, just the fact that it was so corny, it was actually cool, and it ended up amassing something of a cult following at the University of Dundee, because whenever it was parked outside the physics building and I was working on it, there were loads of people who would come up who were genuinely interested, and there were loads of people who asked if I could take them for a spin in it. And even like the most ardent skeptics of it at the time would always get out the passenger seat with this big Cheshire cat grin. They could see actually that was great fun. That was such a hoot to drive or to be a passenger in. And they got it. It was so smooth. It was so nippy. It genuinely scalped taxis and white van drivers off the line. Nice. Because of the amount of torque. It was only 20 kilowatts, but it dumped that very quickly.
What was the motor? I take it was a AC motor, was it?
DC brushed, if I remember rightly.
Okay.
Brushed. So that's annoying, because every now and again you have to change the carbon brushes on it. But it is very much an obsolete design of motor, obsolete design of battery pack. The fact that you had to top it up every so often with deionized water, for example. And it was definitely, the batteries were starting to show their age by this point. There was a separator defect in these Saft NiCad batteries that was discovered in the year 2000, but my 106 was built in 1999. So basically they shorted themselves, but because it was an aqueous system, it wasn't going to catch fire. It was just going to kind of fizzle itself out, basically. So it did end up with the range reducing significantly as this problem worsened. And so the little light on the dashboard saying I need to top up with deionized water kept coming on more and more often. And I would stand at the physics lab with a massive, however many gallon drum waiting on the deionizer. It was quite handy. I was working at a university at the time, piddling fresh deionized water out of it. And I'd be like, 25 minutes later, just like, okay, I'll carry this, put it in the kind of aquifer system that fed all the batteries. And then after a couple of liters, you would just see it kind of piddling the overflow out the underneath of the car going, I'm full. It's like, are you kidding me? You said you needed loads. So, it was a pain, but it was, it was still a great car.
So it wasn't a production car, was it? This was something.
It was.
It was a production car.
Yeah. So PSA, PSA Peugeot Citroën, they made about 10,000 NiCad powered EVs off that same kind of powertrain between 1995 and 2005. So there was the 106, the Saxo, the Berlingo, and the Partner. So you had the two vans as well.
I'm gonna have to swat up on that then, because I didn't know that they, I keep coming across electric cars that were, factory cars, because they kind of pop up. And it does tend to be with the kind of people that I've been speaking to recently, that they're popping up more and more, and they're still going. You know,
Oh,
a lot
yeah,
of them. So, what did you? I think we mentioned you spoke earlier with me about the vehicle that it's had a battery upgrade, or it's getting one.
Yeah. So the 106 back at the sort of beginning of my PhD, I decided to use some of my humble little stipend to upgrade it to something a bit more contemporary. So I managed to get my hands on some lithium iron phosphate cells from Calb in China. That was basically about all that EV tinkerers could get their hands on at the time, bearing in mind that the Nissan Leaf was only just starting to roll off the production line in Japan. For example. So yeah, these LFP cells, I managed to get about 18 kilowatt hours worth in there. And that was good for roughly 70 miles per charge. Although I will admit it wasn't me that did the spannering. It was a more likely than not friend of the channel, definitely friend of friends of the channel, Euan Mcturk, who definitely doesn't get a shout out as much as he should because he's an absolute legend when it comes to anything electronic or mechanical. So yeah, he happened to be just across the Tay Bridge from me at the time and very kindly did the work. So that ended up going from Dundee to St Andrews, where I was doing the PhD at the time, and back on about £1 worth of ecotricity, back when ecotricity was a premium product because renewables were still more expensive than fossil fuels. So yeah, that was my commuter for a lot of that time. But unfortunately, those LFP batteries met an untimely demise. It wasn't their fault. So when the research group moved to Oxford, I had to leave the car behind. I left it with some family, and it was parked on a very steep driveway in the west coast of Scotland where it rains a lot. And the weatherproof cover on the BMS had come loose, and rainwater on a very rainy day managed to get into the BMS, shorted it, and bricked the battery pack. And took out about half the cells, I reckon. So yeah, it was my parents who had it, and they drove it 1 mile down the road, and they sort of from fully charged, and the warning light came on, and they phoned me and said, "Is that normal?" It's like, no, it's definitely not. Return to base, and we'll see what we can do about that. So it ended up going into Dundee Museum of Transport, and latterly Alford, Grampian Transport Museum. But it's now going to get more lithium-ion batteries in it. A good 6-7 years after its hiatus. It should still be running around on those LFP batteries today. They would have been fine, but I decided now is the time to get it back on the road. I miss it too much.
That's fantastic.
The rest of it still works fine. If I could put an iCads back in it would behave exactly as it is, but it just needs a bolt-on BMS replaced for lithium-ion, and then obviously some lithium-ion cells in it. So yeah, that's happening as we speak.
Well, there was, the 106 has always been a great handling car as well. I'm sure the battery packs are heavy, but I'm sure it makes it still a good handling car. Jamie's just jumped on. It says there was a molten salt battery car.
Correct.
Had to be plugged in when not driven to keep it molten. Can't remember where I'd heard of it. Oh, not heard of that one before.
Right. So BMW had one as a prototype, and also Ford had the EcoStar, which was, I think it was the Escort van, early 90s. If it wasn't an Escort, it was something akin to a Ford Sierra van or something. Yeah, and that was sodium sulfur, as Paul's pointed out, molten salt.
Yep.
The problem with sodium sulfur is it's very corrosive. And basically, such as the structure of it, there's these two kind of molten vats, and never the twain shall meet. And if they do, because of the corrosion through that separator, then fire
Bad things
pretty
happen.
quickly.
Well,
so there were
seeing as though we naturally came to the fire. I know we're jumping around a little bit, but seeing as though we you mentioned fire. Now there is a lot of negativity, unfortunately. When will it stop? When will it stop around batteries? I mean, there was. Let's take the most recent example, which was the bus fire in London.
Yeah.
I don't know much about that one, and I don't think the media went too crazy with it. I just saw a little bit about it, but what happened about the bus in London? Was that a battery fire, or was that components, or?
So we don't yet know the official cause of the fire, or at least nobody's told me, and I have been asking about. But from what I've seen, that was not a battery fire. So that vehicle, we've looked at the registration plate, and we know that it's an Optare Metrodecker. The Optare Metrodecker uses NMC cells. Those are the lithium iron, the lithium ion, lithium nickel manganese cobalt oxide cells, which, if they are severely damaged or abused, will catch fire.
Yep.
But something didn't quite add up, because yes, the fire was near where the battery pack was at the rear of the bus, but apparently the fire brigade managed to put that fire out within minutes using conventional equipment. If it was NMC without opening up the back of the bus and so on, that simply wouldn't happen. So there were theories that it could have been something to do with something electrical arcing and catching fire. There were theories about incorrect coolant being used as well, flammable instead of non-flammable. And you can just imagine that there'd be someone at TfL or Go Ahead's depot being pulled up to the fleet manager going, I didn't know that flammable and inflammable were the same thing. You know, it's probably what's happened, to be honest, because it does look quite close to the fuel, the coolant filler cap. And apparently there was a similar issue a few years ago with buses that had been incorrectly filled with flammable coolant. So it probably was something like that. And I'm pretty convinced it would be, because those batteries, without actually opening them up properly and using specialist equipment, wouldn't have gone out in minutes. But
I'm sure that it would have been, I would guess that the battery pack on a bus like that is going to be circa 300-400 kilowatt hours. And if that were to have thermal runaway, then, you know, that would have been a lot more, there'd be a lot more coverage on it, I'm sure. And hopefully, no, you know, thankfully, I don't think anyone was hurt, which is a good thing. Just keeping on the fire side of things for a second, and the battery safety. You know, there's all these new technologies which we've touched upon. You know, NMC has been the most popular battery because it's got such good power density, and it's good for, you know, range, etc. And now we've got lithium LFP batteries coming along, sodium batteries, and eventually, I'm not holding my breath, solid state as well. But what are with these different chemistries, what are the benefits from a safety point of view? I mean, from the little knowledge that I have, I know that LFP batteries and sodium batteries, they can be pierced. Is that correct? And they can be there's a lot more, they're safer.
Yeah. There's a lot of talk about how sodium ion is an inherently safer chemistry, despite the fact that when you did your chemistry experiments at high school, where you drop the lithium in the beaker and it fizzes away, and then you drop the sodium in the beaker and it fizzes away even harder, a sodium ion cell is an inherently more docile chemistry. Now, interestingly, I've not seen any footage of nail penetration tests of a sodium ion cell, but I have seen of LFP. But the point with sodium ion is that they are much easier to thermally manage, and that means that the cooling and heating requirements, because also, by the way, unlike lithium ion, in particular LFP, sodium ion doesn't mind cold weather. It doesn't lose that much of its range. So this cold snap we're having today, you'd still get near enough the full range out of your car. That said, that range would be less than even a lithium iron phosphate EV today. But the point is that with sodium ion, because you don't need as complex a thermal management system, you can shove the cells closer together, and that means that you improve the energy density of the pack. That said, it's an inherently less energy dense cell, so you're making up losses rather than improving over the standard that's been set today. Lithium iron phosphate, if you penetrate that, the most kind of basic ones will vent gas but will not catch fire. But the BYD blade cell is really interesting. So that's one where you can drill straight through it when it's fully charged with a metal drill bit, and that will barely reach 60 degrees C, no gas, no fire. And I'm particularly proud of that one because it's one of my former PhD buddies from Oxford who's now back in China, and he heads up BYD's cell and battery development. And I'm so proud of him because he'll have had a lot to do with that chemistry or with that particular packaging of it. Fantastic. It's interesting to note that there is actually an attempt to make NMC as safe as that as well, which, there's various tweaks that you can do, but one of the more interesting ones I've seen has been the Evonics brake flow design. So that's where you actually change the physical design of the electrode. Instead of having one big kind of sheet of continuous coverage of slurry, basically, that's coated onto aluminium for for the NMC positive electrode. What you have instead are lots of tiny little electrodes, and they're all individually sort of slow blow fused almost. And that means that if you puncture some of that, then yes, that's going to get hot. Yes, that's going to discharge quite quickly. But because of this whole fuse thing, you've isolated most of the rest of that material. So Evonik, they did a pouch cell penetration test with this brake flow design, and it didn't do quite as well as BYD's blade cell. But that's because BYD set the bar so high. The blade cell only reached 60 degrees C. The brake flow got to about 70 degrees C. Oh, heaven forbid. Again, as far as I could see, no gas, definitely no fire. So potentially, if the likes of that brake flow design is adopted, then you would pretty much need to slice the entire cell with a machete right through every single one of those tiny wee rows somehow to get anywhere near the kind of typical NMC reaction.
Yeah.
The other one that's worth mentioning is the Toshiba SCIB, or lithium titanate LTO, to give it its chemical name. So that's a chemistry that you're not going to see in EVs, mainstream EVs, because this is you've replaced the anode, the negative electrode, the graphite, with lithium titanate. And that's not only more expensive, but its potential is higher, and the voltage is the potential difference between the positive electrode and the negative electrode. So you've taken the negative electrode that was right down to 0 volts versus lithium, or near enough, and you've increased it by a volt. So the voltage of the cell is that much less. So it's a kind of 2 to 3 volt cell off the top of my head, rather than like 2.5 to 4.2 volts, that sort of deal.
Yeah.
However, LTO is super power dense. So in other words, it can get lithium ions in and out of there really quickly. So super fast charging and discharging, although you won't get as much range per charge because of that lower energy density. But what happens is if you drill through or short with like a dendrite or something, the LTO material, it does a kind of phase change from being very highly conductive to very highly insulating, and it just inherently passivates itself, so that doesn't become a problem. So again, the SCIBs are very safe cells in that regard.
Something that I heard about the sodium batteries is the fact that they're going to become not only more popular, and they're really good value because of the materials that are within them, but you can actually transport. I heard this boat insurance or something along those lines. When electric cars are transported, if they've got charge in the batteries, then it's a lot more expensive to transport. But sodium batteries, you can put them down to 0 in terms of state of charge, because they can take it, unlike a lot of other lithium, a lot of other different chemistry batteries. So not only is it safer, so the insurance is less, so the transport is less expensive. Is that correct?
Oh, 100%. Yeah, you can put a resistor across the terminals of a sodium ion cell, as you say, take it right down to 0 volts, ship it halfway around the world, and it's basically a paperweight at that point. And then you can recharge it fully, and it's fine. If you try that with the lithium ion cell, you've irreversibly damaged it. You start getting copper leaching out of the anode current collector, and that starts to form some very nasty dendrites and so on. So you don't want to do that. You've physically degraded the cell. Sodium ion, that doesn't happen. So as you've said, it's not only cheaper to make. Incidentally, sodium ion done properly doesn't contain cobalt or nickel. So just like lithium iron phosphate, there's no nickel, there's no cobalt. You've removed some very expensive materials there. And in the case of cobalt, a contentious material. But such as the move towards sodium ion, or the expected move towards it, and the existing move towards LFP, there's actually a forecasted surplus of cobalt by 2030. The reason being that cobalt is a byproduct of copper and nickel mining. So it's going to come out of the same ore, but nobody's buying it as much as they did before. And of course, there's a sliding scale within the EU now, or about to start soon, where if you're making batteries or you want to sell batteries, particularly in the EV sector and the energy storage sector, you need to have an increasing percentage of recycled content, particularly cobalt and lithium. So there's not only going to be less demand for cobalt overall in batteries, but there's going to be less demand for virgin ore and more demand for recycled content of cobalt in order to not be, basically fall foul of rightful punitive measures, because we need to make this a circular economy.
No, absolutely.
So,
absolutely. And this is something that I bang on about with people that, a lot of people still think that, battery electric vehicles are not good for the environment. Okay, yes, there's going to be elements where, yes, we need to, we will create CO2 emissions to make things, because that is what it is, but it will be so much better for the environment, with all the recycling of the batteries and, all the other feeds into making this transport electrified. Question here for Lars. He said, is higher state of charge more of a pressure cooker for triggering internal shorts by internal cell faults?
Yes, I mean there are kind of ongoing studies about the kind of trigger points of thermal runaway and what the kind of worst factors are. But generally speaking, if you're at a very high state of charge, there's more energy contained in the cell. So if it's going to short circuit, it's got a lot more energy to discharge through itself and generate heat, and that heat results in degradation of materials that form flammable gases, etc. But in terms of actually triggering that thermal runaway, you're right that a higher state of charge in an NMC cell is generally bad news, because if you look at the spec sheet for a typical NMC cell, the manufacturer says you can go up to 4.2 volts. Your smartphone manufacturer probably goes, we'll get 4.3 volts out of that, no bother, and that's why your phone dies so quickly. Whereas in like 2 or 3 year battery lifespan before it becomes unusable. With electric vehicles, they probably have that cell voltage backed off a little bit to at most 4.15 volts, maybe 4.1. You don't lose that much capacity as a result, but because the electrode or the cathode potential, the positive electrode potential, isn't as high, you are not feeding those degradation mechanisms as much. So absolutely higher state of charge in NMC. It's the reason why it's recommended that if you aren't going to use your car for a while, if you infrequently use your car, set it to about 80% state of charge, and then run it down to between 50 and 20% state of charge, ideally, before you plug it in again. If you're just going to shallow cycle it, that's not going to do it too many favors. And especially if you're leaving it at 100% and then shallow cycling it by taking it down the shop to Tesco's and back, 5 mile round trip, you're still at like 95% state of charge and you're plugging it in again. That's how you kill a battery. But the battery management system does a very good job of mitigating the worst of that by blocking off the true maximum voltage of that cell, and just basically allows the degradation mechanisms there to slow down, and it extends the lifespan. Incidentally, if you do have a short range NMC electric vehicle and you're using it day in, day out, and you need the mileage, for example, my old 24 kilowatt hour Nissan Leaf, when I was doing a 50 mile round trip, I charged that to 100% every night because I was using it within a couple of hours of the charge completing, so it didn't matter. So yeah, they are a lot more robust than we give them credit for. But if it was a car that I was only going 2 miles down the road and back, I wouldn't be charging it to 100% routinely. I'd be leaving it near 80%. The exception to that rule is lithium iron phosphate, because the cathode potential for it, the positive electrode potential, as I mentioned before, is lower. And that means it's actually just about below the threshold at which the electrolyte starts to degrade against the positive electrode. So actually, that same degradation mechanism doesn't happen as much. Also, lithium iron phosphate, unlike NMC, has a much more stable, flat charge/discharge plateau. So the BMS, if it's looking at voltage to try and ascertain what state of charge it's at, it's a bit of a game of Marco Polo, but the electrode is not shouting polo back. So what it does do at the very end, as it's approaching 100% state of charge, is that voltage upticks quite considerably, and then the BMS goes, right, I know where I am now, perfect. So that's why even Tesla say, if you've got an LFP Model 3 or Y, charge it to 100% as much as you want, because it's a totally different kettle of fish.
No, I've got a much, as you might know, Euan, I've got a much older Tesla Model 3, which NMC chemistry, it's done 92,500 miles. And, I always try and charge it up to sort of 80%. I have recently, because it's been cold, I've been doing a lot of long journeys, getting it down to sort of very like single digit percentages for a battery. So it's good to hear some of the tips that you're coming with. But how bad is it for a battery to bring it down really low, in the sort of 3-4%? Is that not good practice for NMC?
But, yeah, I mean, there's degradation mechanisms that take place at the lower end as well. You're not quite get to the stage of that copper leaching I mentioned before, but yeah, the electrode is not going to thank you for it nonetheless. Therefore, if you can avoid routinely taking it down to 3 or 4%, do so. If you've got the opportunity to charge briefly, then that gets you to the point where you can kind of plug in at near 20%. That's fine. But then again, lithium-ion batteries in EVs are far more robust than we give them credit for. So if it is a genuinely short-range EV, you genuinely need the full range, then go for it. If you're going on, if it's a long-range EV and you're going on holiday, then yeah, charge it to 100% so that you've got an easier job
Oh
on
yeah,
the journey.
yeah.
For example,
I'm not.
yeah,
Sorry, go
yeah.
on.
I know, basically, so with my Model S that I've got, it's an old school Tesla Model S, 2015, 130,000 miles on the clock now. I took that from Edinburgh down to Devon last year, and I
Oh
normally
wow.
leave that car sitting at about 80% state of charge on the driveway. And as I said, run it down to about 50 to 20% and then plug it in again. Obviously, before heading to Devon, I charged it to 100%. It got supercharged a couple of times en route. When I was
Yeah.
at the holiday cottage in Devon, it was charged to close to 100%, so we could go and do lots of exploring. That's fine because that's infrequent, but that's what it was needed to do. And if there was a strategic kind of supercharging stop that was slightly further away than, well, 20% state of charge, you were kind of running it below that, that's fine. It's not a regular occurrence. Don't worry about it. The stuff I'm telling you here is to be a battery health freak, to absolutely maximize the lifespan. You're talking about the
Right.
difference between hundreds of thousands of miles and hundreds of thousands of miles. So yeah, it depends on how much you want to run that valuable object of yours into the ground.
Well, yeah. Well, with EV prices, it's not quite as valuable, but there we go. But following up, I'm plugging it in with friend Andy, who recently checked his 220,000 mile Tesla Model 3. And that was a long range stealth, so it's a performance with the small wheels. And the one that was recently on the Cleveland EV channel, Kate and goodness, it's gone out of my mind
James
now.
and Kate?
James and Kate, yeah. Had a long day. And yeah, it was still 85% for 220,000 miles for the same battery. Really impressive. We've got a question here from Foxdown Follies. Is this why LFP gets more cycles than NMC?
Oh yeah, so that will be to do with the maximum potential of the actual cathode material itself, the LFP versus NMC. That'll inevitably be part of it, yeah, because you've not got that loss of electrolyte and that loss of lithium inventory, it's called, because the lithium again gets mixed up in that degradation as well. Plus, LFP is a totally different structure from NMC. It's not like you just kind of swapped some elements out. It's a physically different structure, and that's where it's an olivine structure versus NMC that's not olivine, and that's where my PhD buddies who came from a chemistry background would have immediately be able to picture that. But that's where my kind of well-attacked Jenga block sits in terms of trying to draw that structure on a piece of paper. But it is a different structure. It's more resistant to degradation, to physically being kind of battered apart over time. But also, yeah, exactly, it's inherently, whilst we're dealing with electrolyte that is somewhat suboptimal for NMC because it does degrade at a very high state of charge, but we use it anyway. And obviously, the higher that voltage goes, the more that electrolyte degrades. But that electrolyte is good for LFP because it's not crossed that degradation threshold. So that means inherently you're going to get more life out of it. So yeah, absolutely. Good question from Paul. Actual capacity versus usable capacity. This is very much dependent on the EV.
Absolutely, yeah.
Yeah, because the state of charge buffers that you find in a BMS are very different from EV to EV. So, you look at the 30 kilowatt hour Nissan Leaf, it was notorious because its buffers were too small. So the ones that were, kind of basically one careful old lady owner leaves it charging to 100%, takes it down Tesco's 5 miles and back once a week, and then plugs it in again, is just kind of waterboarding it to death with electrons. Whereas, you look at, I mean, to be fair, also the BMS was incredibly pessimistic about the state of its battery. So there was a software update that corrected that. So you miraculously regained capacity. It was like, actually, it was just kind of a bit pessimistic about its true state of health. Anyway, the point is that you compare that to the poster child of over-engineering, which is the Chevrolet Volt or Vauxhall Ampera E. Vauxhall Ampera, not to be confused with the Ampera E. So yeah, Chevy Volt, Vauxhall Ampera, that had a state of charge buffer at 80% of its true capacity for the top end and 20% of its capacity for the bottom end. So it only used the middle 60% of its true capacity. And that's why there was one over in the States, which was owned by a GM employee, which had done 400,000 miles, and the battery was still allegedly reporting 100% state of health, or at least 100% usable capacity. It may be that the BMS had gone, okay, we can start eating into these buffers as the capacity shrinks, because it's on the way out, but we can at least preserve that kind of experience of having that amount of range. That remains to be seen. That's something else that some manufacturers will do. They'll reduce the buffers as the pack starts to degrade. But, in terms of that, to be honest, actual capacity is more of a concern than usable capacity, because that 3% usable capacity, you're also adding on the handful of percent at the lower end that's already been blocked off by the BMS. So actually, you're only taking it down to maybe kind of 8% of its usable capacity or higher. So yeah, great point by Paul. And that again kind of emphasizes the fact that a modern, and by that I mean within the last 10 to 15 years, electric vehicle, 99 times out of 100, depending on the make and model, does a pretty good job of looking after its battery pack, keeping it at its optimum temperature, its optimum voltages, making sure that real abuse conditions are not possible by human intervention. So you cannot physically break it by driving it, break the battery by driving it. You'd have to do something spectacular to really affect it. So yeah, I mean, they're far more advanced. The battery management systems in an EV are far more advanced than the ones in your phone or your laptop, for certain.
Yeah. No, it's interesting because I have heard that the Tesla usable is a lot higher than higher than a lot of other EVs. But there was a truck that come across recently, a Volvo truck, where the battery was 540 kilowatt hours and the usable was 370. There was such a buffer there.
It's like 2 standard
crazy.
range Tesla Model 3s worth of buffer.
Absolutely bonkers. Yeah.
Why would you, I mean, if they're using if they're using NMC with that, and then doing a massive buffer, then they'd be as well probably using LFP. Although they might be going, oh, we're worried about cold weather performance, in which case, just get good at thermal management. That's what Tesla's done. The standard range Model 3 and Y, which are LFP, seem to be doing pretty well in Norway, which, funnily enough, gets very cold in winter. So,
This is an LFP, mate.
Really? What the heck? Okay, yeah. I genuinely do not understand.
I'm sure is it the same one? Looks like it's the same one. Oh, 2000, or maybe that's 2019.
Maybe not.
I'm going to look into that. We'll come back to that. But is it true that Tesla don't have too much of a buffer? And I actually thought the buffer was just at the top. I didn't realize it was the top and bottom. So that's new for me, for sure.
Oh no, definitely. Yeah, they'll definitely block off a bit at the bottom too.
Right.
So your lithium-ion cells will all start to really fall off a cliff voltage-wise as they approach 0% usable capacity. So to be honest, you're not losing a huge amount of capacity by setting that voltage limit higher, like 2.7 volts or 3 volts instead of 2.5. The car may allow it to dip underneath it under high load, but at lower kind of, so basically when you're going into kind of turtle mode, it might allow you to dip slightly below it, but not with any, not for a prolonged period of time. Again, these are the kind of secret sauces of the individual EV manufacturers. So I've been able to, there are people who have been able to break into different kind of battery management systems. I say that it's basically just sniffing the CAN bus and seeing what the cell voltage readings are up to and so on. But in terms of the exact battery management protocols, that tends to be a closely guarded secret. But yeah, as for Tesla, they do tend to take the upper buffer pretty thin, even on the NMC or NCA stuff. NCA similar but different. So that's why if you routinely charge a Tesla with an NCA or an NMC battery over 90% or at 100%, that warning message comes up on the dash and says, if you keep doing this, you'll accelerate the degradation of your battery, just so you know. And it lets you be your own engineer and assess your own level of risk that you want to take with that vehicle. But just remember, if that pack was to fail within warranty, they will know that you've overridden that message a shed load of times, and they'll probably be able to push back on that. So, it's an interesting kind of warranty feature as well as an engineering feature that does have a legitimate value to the extension of the lifespan of the battery.
Yeah. We've got another question from Lars. What are the early warning signs degradation has come to a level where internal self-faults are more likely to happen?
So if you have access to the cell voltage readings, you'll see one or two of them starting to dip lower during discharge than the rest of them, or dip higher during charge than the rest of them. They'll start to go out of sync in that regard. And we've certainly seen that with Nissan Leafs. There was a spate of them that had a couple of sort of faulty modules. I say a spate of them, it was a handful of them, but there was one person who had the presence of mind to tweet about it quite a lot. And I got involved in trying to help. The dealership kind of pleaded, not ignorance on it, but they said everything's fine. I told them, get Leaf Spy. And it looked like a flipping roller coaster. The cell voltages should have been like that. And, there were two that were just up here somewhere. And I said, or down there somewhere, I should say. And it was like, why have they not realized that this is well out of whack? You've got a faulty module. So
it is scary. It is scary. The dealerships are so out of touch with electric cars. It's scary stuff. I think a lot of them, there's the odd person that is interested in electric vehicles in dealerships. And I think a lot of them tend to have gone into some specialism in the EV industry and left the motor trade behind. Very similar to myself, in fact. But yeah, every time I talk to anyone in dealerships, the knowledge is so poor, which is
true.
I mean,
some cars are better than others in terms of letting you know when something's starting to go a bit wrong. So Teslas, for example, will say, the maximum state of charge for charging has been limited, reduced motor power, perhaps. Those will be the kind of indications that something's not quite right. And it's normally because a module has failed on one of their oldest and kind of poorer designed Model S, as he says, with an old one sitting on the driveway. So touch wood, mine will be fine. But
which battery have you got?
The problematic one, the 85. So that's the one. There were a couple of thermal runaway incidents that were isolated incidents, but Tesla, out of an abundance of caution, limited the supercharging speed on the 85 kilowatt hour packs. So they're a good 20 or 30 kilowatts lower than they were, maybe more. For a given state of charge versus when they were new, purely because they were just worried about overdoing it with those cells. To be honest, it was like one or two of them were like cell production defects, but the other issue was that the air conditioning condensate pipe was initially routed to sit atop the battery box, and then the water would just corrode through and it would take out one of the modules. But allegedly, I'm assured by Tesla that mine has not been affected like that. I'm pretty sure I've got it in writing somewhere. So if it turns out that is the problem, when it eventually meets its maker, then I will be bringing that up with them. But the point is that there were a few kind of mistakes that Tesla made when they were brilliant at making a battery on wheels, but they weren't as good at making a car. They are obviously catching up now, and they're getting better at making the car as well. But it's the 85 is the one that occasionally had the condensate drain issue. That's the most kind of common way that those packs get taken out. And they tend to be charge gated, so that means that their supercharging speed is lower. But that said, they do have free supercharging for life unless they've gone through a Tesla dealer. So there's swings and roundabouts. You're sitting at a supercharger for an hour, but you're not paying for it. So
you've got one of the free supercharged ones, have you? Nice work. Nice work.
My shrewd investment.
I know we've already done an hour, but one thing, if you're okay to talk about, Euan, is I'm really keen to talk about your interest in EV conversions. Now, you've obviously had somewhat of a very exciting electric car, being the 106, quite a unique individual beast. You got the Tesla Model S 85. Was it a dual motor or single motor?
No, single motor, which means that there's an insane amount of luggage space in the front. In fact, shameless plug. So the Faster Project YouTube channel, Faster Project, they installed, it was an EU funded project that installed 75 rapid chargers across Scotland, Northern Ireland and Republic of Ireland. But as part of the public outreach for that, Rick Boulemere and I did some EV reviews, and there's an old Tesla Model S versus a new Tesla Model 3 that we did a side-by-side comparison. I donated my own S for that one, but at the beginning of the video, you see just how much storage space there is in the frunk on that. It's insane. So yeah, actually, it's a shrewd investment if you've got a lot of stuff you need to carry back to. I don't know, if you're going to visit the family over Christmas and there's loads of presents and stuff, you never run out of room. It's great.
Well, you appreciate this, Euan, because I know you've got a bit of a musical background, like myself. Is the fact that I started talking to a guy who had a slightly modified Model S, and he was a violin teacher, and he did something to do with making violins. And he says he can get a double bass in the back of a Tesla Model S, and that's the reason he bought it. You know, so yeah, lots of space. Yeah, so you've got got the Model S. You've got a couple of other cars, and you mentioned also that one of these cars you're thinking about doing some exciting things with. Can you explain what you're going to be doing with your current car?
Yeah, so there's the less interesting one, and then there's the more interesting one. And the less interesting one is actually powering this conversation just now. So it's a Nissan Leaf 30 kilowatt hour that's on an Indra V2G charger, and that's been absolutely brilliant. So that gets charged up on Octopus Go, 9.5 pence per kilowatt hour overnight, and then it just powers the house for the rest of the day. So I'm saving over 20 pence per kilowatt hour for my waking hours. And then on top of that, with the solar panels, it can load match the export from them over summer. So between the V2G charger and the heat pump and things like that, all of our, heating, electricity, hot water is free for most of the summer. It's great. It's basically a battery on wheels that I can drive to Tesco if my other half's taken the Model S to work. But the other car is a Mark I Honda Insight. So that was a bit of an impulse buy, because when Evan was upgrading my 106 to LFP, he turned up at my house in his kind of British Rail blue Mark I Honda Insight. And I went, okay, that's pretty cool. Tell me more about that. And the idea just kind of stuck in my mind. And I found one for sale that was in the citrus, the launch color, that kind of light greeny yellow color.
Wait, I think I've got a picture here.
Go for it.
Yeah, and I often see this car on another popular YouTube channel, Late Break Show, because Johnny's got a 330,000 mile one, hasn't he?
Yeah, he has. Yeah, identical.
In a very fetching yellowy color.
Yeah, it's being colorblind. When I bought it, I genuinely thought that was gold. And then I had the news broken to me, it definitely wasn't, but oh well. So that used to, when I was based down at WMG, University of Warwick, massive battery and EV research facility, that used to do the 330-mile trip from Coventry to Edinburgh and then back again, so 660 odd miles for about 50 quid's worth of petrol, 70 miles per gallon at 70 miles an hour without even trying. Personal best on the motorway was 101 miles per gallon. Not miles an hour, but that ended up in a transport museum next to the 106, because when I got my 24 kilowatt hour Nissan Leaf Busby, that's in the Plug Life television episode about the road trip to Skye in a short range EV. I mean, as that video showed, Busby, the Leaf, the short range Leaf, was far more versatile than I thought it would be. I'd basically bought it as a like for like replacement for the 106, which can't rapid charge. It's only like a 14 amp onboard charger. So I expected it to just be doing local runs, but it ended up being so versatile that the Insight basically never got run. And it just kept seizing up on the driveway. And it became more of a hassle than anything. So I ended up sticking it in a transport museum too. But at some stage in the not too distant future, it's my fullest intention to basically remedy the problem that I had with it. And that was that this was not fully electric. There was too much to seize up. So the intention is to retrofit it to fully electric with at least 40 kilowatt hours, ideally more, of battery capacity. I'm going to aim for a 200 plus mile range. And also not just rapid charging capability, but vehicle to grid capability. So that means that my Leaf can be sold on, and that'll free up a bit of space on the driveway, which is very, very quickly starting to resemble that 1970s sitcom Butterflies. I don't know if you remember that one.
No, I don't.
So
it means you've got not enough space outside and too many cars. Just to give you a little flavour of that, Euan, I made a driveway in the front area of my garden to facilitate another vehicle. That's at the point where I'm at the moment. So,
I don't want to eat into our nature garden, so it's just one big long skinny driveway, which is the same as in Butterfly. So it started. Was it Nicholas Lyndhurst, the guy who played Rodney in Only Fools and Horses? So he was, he was in it, but
I think I
basically he
know the
was
one
like
you
the
mean
son
now.
and the
Yeah,
family.
yeah.
Yeah, and inevitably, whenever someone needed to get the car, it was the one that was at the very back of the driveway, so everyone had to get out and move the cars, and that was like an ongoing, oh, ha ha ha, what we found funny in the 70s sort of joke. Anyway, yes, that's basically what happens, and in my house, if I'm needing to get one of my cars out, so it's getting to the silly stage. It would be good to try and free up space and kind of condense the collection so that it's the sweet spot between cool rare vehicles and clever party pieces. So
yeah,
Mark 1 Honda Insight, of which there's only about just over 200 in the UK, that is fully electric and does vehicle to grid and rapid charges quickly and all of this. That would be the sweet spot for that one, and is in that citrus color with matching bucket seats, by the way. The interior matches the exterior on it. So I love it. Need to get it back on the road.
Fun enough, Johnny Smith was talking about things that he was doing to his Insight, and apparently there's a few things you can do to the rear suspension to make it. I don't know if you watched that episode.
No,
watched the last episode. I think there's a Honda one. There's one before where he talks about his projects. Check it out, because there's a few little things, maybe some tips for the Insight there.
Interesting.
And so what motor are you thinking about putting in the Insight then?
This is where I'm going to throw it open to the floor. I'd love to get everyone's thoughts in the comments. I know Paul Compton, the immeasurable font of knowledge that is Paul Compton, has previously suggested. Well said, Fox Hans Follies. But I know that previously the Mitsubishi Outlander plug-in hybrid rear motor, I think, had been suggested, and also the Nissan Leaf motor too, which are definitely both under consideration. The Outlander system voltage is a little bit lower than the 400 volts that the Leaf is used to, and that I would intend to use. The other one I'd love to put in there is, ideally the Tesla Model 3 front motor, but there doesn't seem to be any way to control that on its own, because it takes so much control from the rear motor that kind of has the guts of that control built into it. You can see this is where my knowledge on sort of mechanics and electronics reaches a hard wall, and I know that there'll be a lot of people face palming themselves watching this now. It's like, he doesn't know what he's talking about. It's so infuriating. So I apologize, but basically the Model 3 front motor being reasonably small, and also because the Model 3 is such an efficient car, I want to maximize the efficiency of this. Yes, I could probably get 200 miles per charge with a Nissan Leaf motor, but the Nissan Leaf is average in terms of its efficiency. It's about 3.5 to 3.8 miles per kilowatt hour when it's in a Leaf. Yes, it's going into a lighter car, which means it would probably do about at least 5 miles per kilowatt hour. But why not aim for more? Let's see if we can get past the likes of, or close to what the likes of the Lightyear Zero or the Mercedes EQXX would be. A bit ambitious, but the efficiencies that they could achieve, I would love it to get somewhere near that, because the Lecky bill for any kind of cross-country trip would just be dirt cheap at that point, and you would genuinely be saving easily hundreds and hundreds of pounds a year just running that car versus a Model S, for example. So Jamie's EV conversions, that's very useful intel, actually. There's a couple of people who have said that the Outlander motor does seem to be happy at 400 volts. So I will take your word for it, and if anything pops, I'll be straight on the blower to you. I already have a Model S motor. Yes, Zoe, the issue is I also have a Model S, and I kind of need that whilst...
Well, yeah, you got the whole package there, just in case.
I do.
There we go. Open Inverter has the info.
Good shout.
What's this? And then check out Engyro. Is your budget allows it? Okay. Well, all I would say, and this is a big learning curve from my electric TVR project with Ralph, is just make sure it's been used before in a certain combination, just to make life easier. Jamie's a good person to talk to about it, I'm sure, and obviously Paul as well. No, that's great stuff. If you've got enough time, have we got enough time to very quickly just talk about the future of batteries in solid state?
Absolutely, yeah. So solid state is coming. It's coming a bit slowly. It is actually kind of here already. So there's a company called Blue Solutions that has what could probably be described as a kind of early prototype semi-solid state battery that's already been used in the blue car electric rent-a-cars that you used to get in London. and sadly, which have fallen by the wayside, but they're now used in Mercedes electric bendy buses. There's the option to buy the longer range version, which has a modest improvement in range, not as much as you'd expect from solid state, but it has a slower charging time. So solid state, again, done properly, and there's such a broad church, just like lithium ion is a broad church of chemistries. Solid state, in terms of the way that it goes about being a solid state cell, is a broad church of approaches. So what you're doing is you're removing the plastic polymer separator and the liquid electrolyte within a lithium ion cell and replacing it with a kind of 2-in-1 solid component that is the electrolyte, and it allows the lithium ions to go between the cathode and the anode without allowing electrons through, without shorting the cell. So you get ceramic solid state electrolytes. Those are great at allowing lithium ions through very quickly, but they're brittle. So if you're driving it down the cobbled streets of Dundee in a taxi, you're going to break it apart in no time.
Yeah.
Whereas you've got polymer electrolytes as well, solid electrolytes. But polymer is obviously a lot more flexible, but it doesn't let lithium ions through particularly quickly. So it's a low power application that it would be suited to. There are attempts to kind of hybridize these, and that means that you get the best of both worlds. And then there are interesting companies like QuantumScape who are invested in by Volkswagen. That's one of many companies which typically, I do keep abreast of the most innovative ones, and every single solid state company apart from Blue Solutions and QuantumScape has just gone poof as soon as you mentioned it off the top of my head. But there's just so many different approaches that I've seen in recent months and years, and there's inevitably loads of companies still in stealth mode. There are so many big automotive manufacturers invested in solid state as well that it's bound to happen. It will probably be some sort of cheats solution initially, like the Blue Solutions thing, which is solid state, but it's better in some ways, not as good in others. But fundamentally, there's talk about being able to use a pure lithium anode with solid state electrolytes, because in theory, they should be resistant, not necessarily proof, but heavily resistant to that dendrite growth puncturing them. So they'll actually allow the lithium ions to kind of coat more uniformly on the anode. The advantage of a pure lithium anode is that is 100% of that material taking part in the reaction and storing energy. You're not storing the stuff that stores the energy. So you don't have your silicon, you don't have your graphite or anything like that. The other thing you can do is you can have a so-called anode-free cell, where what you do is a lithium ion cell is built in the discharge state. So there's excess lithium in the positive electrode. And then the first thing that gets done to it is it's charged up during its formation. There's a few kind of charges and discharges it does in the factory. And what you could do then is instead of having a lithium foil onto which more lithium is pasted during that charging procedure, you start off with a bare copper current collector, and then the lithium ions kind of tracy emming onto it, just kind of splatter onto this current collector. And then you've got just enough lithium to take part in the reaction. And as a result, you've saved even more raw materials, you've saved even more weight, even more volume, even more cost. But basically, looking at the various different versions of solid state, if you were to combine all of their best properties, and this is unlikely to happen, certainly for a few years, there'll be some that will be good at some things, but not others. But in theory, you're looking at super high energy density by using some sort of pure lithium or anode-free cathode design. You're looking at, obviously improved safety as well. You've removed a flammable electrolyte for starters, so it's a lot safer in that regard. You're looking at super high charging speeds, allegedly, with some designs. Excellent temperature tolerance, although interestingly, some of the earliest solid state designs only really worked above 30 degrees C, so you had to keep them warm. Whereas molten salt cells that were discussed earlier, you had to keep them at 300-400 degrees C, something like that. They had to be constantly heated. Wow. And if you left the car unplugged for a few days, you had to plug it in just to heat its, basically melt its battery again. This was just kind of like a gradual kind of increase in temperature. It'd be great in the Middle East, but not in not in the middle of Scotland.
Recent weather. I see. Zoe makes a good point there. We've only got 5 likes, and we had 15 people watching. So please like the video. It really helps the channel, and it really help promote this video, especially for people that want to learn more about batteries. So with what makes me laugh is Toyota. They've been saying, you know, about 8 years ago, I think it was, yeah, we've got solid state batteries just around the corner, you know, and they're lobbying against all the electric cars and, you know, promoting petrol cars. And just to finish off, I mean, it'd be great to hear a little bit about what you're doing, Euan, because I know you're doing so much great work. I think mainly with Fully Charged Live. Is that right in saying, in terms of the myth busting and the was it no BS?
Oh, yeah, it's stop burning stuff. Yeah. So
stuff,
yeah, I'm part of the squad for that. We did our launch event in Westminster towards the end of last year. So Quentin Wilson, Robert Llewellyn, Lorna McAteer, fleet manager at National Grid, and deputy director, I believe, of Association of Fleet Professionals. Just probably the best fleet manager in the country, a formidable force when it comes to EVs. So yeah, great to share the stage with them and to bust many myths. So that's on YouTube. It's on the Fully Charged channel. You can check that out. I've also recorded other episodes with Fully Charged. So there was one recently with Imogen where we discussed some of the most exciting battery technology that's coming up in a bit more detail. So yeah, that's one of their most recent episodes. But aside from that, there's basically, you know, having been a lab-based electrochemist for the first sort of decade or so of my career, I then started working on Plug Life Television, my humble little YouTube channel, to explain how batteries work. Oh yeah, there we go. That's the Fully Charged episode there. Check it out.
I've not listened to that one, so I'll jump on that after this, actually.
No problem. But yeah, also, like, Plug Life Television was founded in 2018 because that was basically, lots of people had good questions about EVs and batteries. Some of them were, you know, kind of, yeah, phrased in a very skeptical light, or just incredibly outright sort of naysayer, they're rubbish because of this. But some people were genuinely asking really good questions, and the people on panel sessions I was watching didn't really have the answer. And it was like, well, I'm a battery electrochemist. I know these answers, and I know that the situation's a lot rosier than people might think. So I started putting together videos that explain how batteries work, and also kind of various other videos, like various EV success stories. That one front and center there was our Elbil road trip in Norway. So Elbil is Norwegian for EV, showing just what was possible in the country that has the highest EV uptake per capita. Incredible what they've managed to achieve. But yeah, loads of techie videos that explain bits of terminology, bits of kind of wider EV tech, and also, of course, how batteries work, and then bust several myths along the way. And then in 2020, I founded Plug Life Consulting. So that's my day job now. Such was the success of my humble little YouTube channel. So yeah, I'm now working on a whole host of technical, strategic, project management and public outreach projects to do with battery tech, EVs, charging infrastructure, and energy storage systems. So, you know, I'll be speaking to strategists about what's the latest chemistries coming up, where's the mineral investment required, where's the processing capacity required, technical requirements, what's the best solution for your application. You know, do you know who's working on this, who'd be able to kind of help with this? Can you help to design it? And then public outreach. One of the videos that you may have seen the thumbnail for was an EV review with Faster Project, which of course we covered earlier. So basically, Plug Life Television, but with a budget, is the kind of public outreach side of things. But on that note, there hasn't been an episode of Plug Life Television for about a year because I've been that busy with Plug Life Consulting, and also the kind of guest appearances on channels such as Chargeheads, of course. But so thanks for having us on. It's been great because I haven't needed to do any editing or kind of infographic creation, so it saves a lot of my time. But the crucial thing is, keep an eye on Plug Life Television, because there are some new episodes coming that are going to look very, very different. Some of the basically they are pilots that will show genuinely what Plug Life Television would be able to do with a budget. And rather excitingly, for that, I've teamed up with the former creative director of Fully Charged, who's also worked very closely with Johnny Smith on the Late Break Show and with Ed China as well. It's the formidable Mark Taylor Hankins from Round Productions, who I just happened to be in Bristol one day. He's based down that way. He said, "Hey, I love how you do technological deep dives. Can we go and talk to some cool EV companies around here?" And just kind of do an almost BBC Four style, you know, just kind of sit down and discuss this tech and what they're up to.
That's brilliant.
proper, professionally filmed, being edited as we speak. And yeah, you bet, if we got a budget to properly do that, we would be up and down the country looking at the most cutting edge stuff in academia and industry. And I cannot wait for that to happen, because I loved doing those pilots. So yeah, watch this space.
Brilliant. That sounds really exciting. So yeah, Euan, thank you very much for giving up your time. I know you're really, really busy at the moment. Thanks everyone who was been watching, and if you've missed the beginning, go back and you can watch it again. All 18 people at the moment that are watching, please give it a like. Really helps the channel, really helps promote Chargeheads. So yeah, thank you very much to everyone. And yeah, if anyone's got any questions, feel free to whack it on the socials, whether it's on the Facebook, Instagram, there's TikTok, so many different socials now, even on X. And just to say, next week we have got Peter Melville from Hevra on, Hybrid Electric Vehicle Association. So we're going to be talking about electric vehicles in non-main franchise dealerships, so non-main dealer dealerships, which will be really interesting, talking about servicing, talking about repair. So that would be really interesting to see. And on, oh goodness me, we've got another EV monthly meet, and excitingly enough, it's going to be on a Monday evening, and it's a specific EV event at Caffeine and Machine. Let me just jump on the diary. It is on the 5th of February. It's actually at both the Caffeine and Machines. I'm going to be at the Hill, but the Bowl is also having one, which is in Bedfordshire. So anyone's at the Bedfordshire one, please take videos and hashtag Chargeheads UK. Make sure you add us on there. But thanks once again, everyone, and thanks again, Euan, for being on today. That's great.
Thank you very much. Cheers.
See you soon, buddy. Thanks, everyone.